so let's return to the analogy of the dog in the well. And yes, it is an analogy. Oftentimes students will ask, did your dog really fall in the well? No, my dog didn't really fall in the well. Of course not, right? I just developed this idea of a way of thinking about it so let's visualize what's happening with the photoelectric effect. All right, so the dog is stuck in the well. That's to represent the electron that's stuck in the atom. So the dog is like the electron. We threw the rock in to get the dog out, but we represent the rock as the rock is representing a photon, a bundle of light energy. And of course, the depth of the well is that's sort of like the minimum energy to get it out. So we're going to transform this equation, which we developed, telling about the kinetic energy of the dog coming shooting out of the well, based on how much energy the rock had coming in, minus whatever minimum energy was get out. We're going to transform this into an equation we can use for photoelectric effect. So we're going to replace Ke dog with Ke max. Remember, when light hits the positive plate and the oppositely charged parallel plates, electrons come shooting off with a variety of energies. We're taking away the maximum energy, that's what we're measuring. The rock is represented by the photon, and here's our minimum energy. And Einstein developed an equation for a photon. E photon was HF, so we replace that here. Our symbol for minimum energy here is going to be this. This is the lowercase phi. Capital Phi is what we use for flux. This is just like a circle with a single slash through it. And we're going to go ahead and box this equation in. The name for phi is work function, which is probably the worst name in all of physics because this doesn't tell you anything about what phi actually represents. There's no good reason for calling it work function. Now, I hate to admit it, but here is actually one place where chemistry has us beat. Chemistry actually has a much better name, more useful name for phi. And those of you taking chemistry, you should already know what that is, because this is the minimum energy to get an electron out of an atom. Right? And when an electron leaves an atom, well, now the atom is not an atom anymore. It's an ion. So what's this called? This is really ionization energy. But we're going to keep calling it work function just because, I don't know, some sort of historical reason. I don't know what that reason is, but we're going to keep calling it work function even though it's not a very good name. Okay, so Einstein had this fantastically different idea that light could be imagined as if it were composed of particles. It's not actually matter because light doesn't actually have mass, but it acts the same way as matter does. When it hits metals, it's knocking electrons off just like actual physical objects might knock other objects away. Some sort of like collision, like when I throw the rock in and the dog comes out. And yet we spent a whole lot of time proving that light wasn't a particle. Remember, we did all that stuff to prove light was a wave. So here's where things started getting weird. This idea really broke open a whole new branch of physics called quantum physics, and we now know that light really has a dual nature. We call this its wave-particle duality. So all the stuff we've done before doesn't go away. We just have to qualify it a little bit. So of course, light is a wave. Of course it is. We went through all the four defining properties. We proved it reflects, it refracts, it diffracts, it interferes. Light is absolutely a wave when it acts like one. So if you observe light doing wave things, diffracting through an opening, interfering with other sources of light, it's absolutely a wave, because that's what waves do. But now Einstein is saying, and rightly so, that light is a particle when it acts like one. So if you observe light doing particle stuff, hitting metal and knocking electrons off, well, that's what a particle would do. Waves don't act that way. Waves can't do that. And so light has this dual nature. It's a wave when it acts like one. It's a particle when it acts like one. It's never both at the same time. That would be too weird, although things are going to start getting very weird in this topic. It's just one or the other, depending on what you're observing it doing. All right, so let's try some problems here. We're going to put some of these equations into place here, right? So let's take a look at number 1 here. So go ahead, read all number 1, pause the video, try it completely on your own, and come back and then see how I do. Okay, so we only have a couple equations to work with here. We're finding the maximum kinetic energy, and we're given the wavelength of light, and we have the work function. So we know we're going to be using this equation, Ke max equals HF minus phi, where phi, of course, is this work function, here given as 4.73 electron volts. That's every different metal, has a different work function, different minimum energy to get electrons out. However, notice that we're not giving frequency, you're giving wavelength. Now, certainly you can do, your conversion, your equation, but you know what? I'm just going to combine equations. We know that C equals F lambda. Now, of course, you can write V equals F lambda, but we're talking about light, so we replace it with C, and we'll assume we're in a vacuum or in air, unless we're told otherwise. So we're just going to go right ahead and replace F with C over lambda. Just combining equations here, just so we can put it all in one shot. Okay, so we have our value of h. It's going to be 6.63 times 10 negative 34 joule seconds. And here, of course, is the speed of light in a vacuum, 3 times 10 meters per second. And here's our wavelength, which is given in nanometers. Remember, we usually put things in nanometers because we want to compare it to visible light. Remember, visible spectrum is between 400 and 700 nanometers. We see this is not visible, but still it's in nanometers to make comparisons. And, my advice is always to, instead of doing a metric conversion or moving decimal points around, just replace the metric prefix with its power of 10. Nano is, of course, 10 to the negative 9th. Now, I paused it here for a second because if you just do this, things are going to go horribly wrong because we have to worry about our units. Just like we converted nanometers into meters, we have to say, wait a second, this energy would be in joules, because the meters go away here. We're going to, but this is in electron volts. We can't do that, right? So we have to do a unit conversion. Luckily, we recall that every electron volt is 1.6 times 10 to the negative 19th joules. So we have to do a unit conversion. That's going to be one of the major hurdles in this topic, just keeping very careful track of your units. If you don't, you're going to get some results that really don't make any sense. Now, certainly here I converted it into electron volts to compare to this electron volts, but I could have just as easily converted this into joules. And if you did that, there's absolutely nothing wrong with it, because the problem never says in which units to report your kinetic energy, and I'll give both answers. But if you didn't get this far, go ahead and try it. We should be getting 1.49 electron volts. However, if you did it in joules, we get 2.38 times 10 to the negative 19th joules. So you can see, just as we always did, electron volts are easier to use. This is why we introduced the electron volt, because this number is so much easier to write and say than this number here. And so, not going to say you're always going to convert into electron volts, but it's a useful unit to use. All right, letter B, you want to find the stopping potential. So now is the time to use the other equation, Ke max equals EVS. Now there's the long way and there's the short way to do this. Which one do you want? I bet you want the short way, right? Yeah. Because remember, the whole point of the electron volt is ease of use. That when one elementary charge goes through an energy change of a potential difference of 1 volt goes through an energy change of 1 electron volt. And so if the kinetic energy is 1.49 electron volts, that means the potential difference to stop it is just 1.49 volts, right? That's the usefulness of the electron volts. You don't have to show the work for that. You don't, right? Now, certainly you can, except you can just be multiplying and dividing by this same conversion factor, so why bother? So as long as it's a single elementary charge, which of course is the case for electrons, the number of volts is the same as the number of electron volts that it went through. It makes sense. All right, for letter C, you're just putting the numbers in, and this time all you're doing is you're changing this wavelength to 500 nanometers. If you didn't try that yet, go ahead and do it. Still using this HF minus phi or HC over lambda minus phi. But, yeah. We get a little bit of an uh-oh here, right? Negative 2.24 electron volts? I hope you recognize that that's an uh-oh, because you can't have negative kinetic energy. That doesn't make any sense, and yet that's what the math shows us here. So, if you haven't thought it through yet, pause the video and think, what does this mean? What's the meaning of getting a negative kinetic energy? Pause the video and really think it through. Alright, so what did you come up with? Hopefully you realize this is saying that something went wrong here, right? That HC over lambda was too small compared to phi. Well, what does this represent? Well, phi number is like the depth of the well. HC over lambda, or HF, that's the energy of the rock, right? That means that this is like when we threw in the 300 joule rock and didn't get the dog out. So what's actually happening here is that electrons just don't get knocked out. The energy of the photon, in this case represented by HC over lambda, was just too small. It didn't beat phi. So we don't report an answer here. You never get a negative kinetic energy. That has no physical meaning. The meaning here is saying that this wavelength of light, 500 nanometers, didn't have enough energy to knock electrons out. So that's what it means here. Alright, just going to pause before we go on to number 2 here, because you'll notice that a couple things here happen with units, right? We have H in these units, joules times seconds, except in these two problems, parts A and C of this problem, we really want it in electron volts, and so it behooves us to just go ahead and do a unit conversion. So if you want to just pause the video and try the unit conversion on your own, that's great. If not, I will give you the value of H in other units. So when you do the unit conversion, we get 4.14 times 10 to the negative 15th electron volt seconds. And so this is a much more useful version of H in this situation if you're going to be answering electron volts. And there's no reason to constantly do the unit conversion. So just, we can always identify this as just another version of H. You'll notice also in letters A and C, we had to use the value of H times C, which is going to happen a lot also because, while yes, frequency is the original term in the equation, very often you're not given the frequency of light, you're given the wavelength. And since you're always going to replace frequency with C over lambda, the quantity HC pops up often enough that actually it's a good idea to just multiply those together and get them in proper units. Now here, you can try it on your own. You're going to get it in terms of electron volts, and also you want to get the wavelength in terms of nanometers, because that'll provide you with numbers that are easy to use and easy to compare to the wavelengths which are often given in units of nanometers. So if you want to try to pause the video and try it on your own, that's great. But I've done it for you. You should get 1240 in 3 sig figs electron volt nanometers, which I know are weird units. This doesn't have any real physical meaning to it, but those are the units that are going to make everything work out quite nicely. So I'm going to box all 3 of these in, and if you were handing in packets, you're also going to box all 3 of these in as constants. Alright, so now we're going to go ahead and try problem 2. So go ahead and pause the video, try it on your own. Oh, in case you were confused about this, the cutoff means the minimum, or the frequency, the minimum energy to get the electron out of the atom. Just barely get it out of the atom. So here we're taking the equation, Ke max equals HF minus phi. And if we're at the cutoff, that means that we just barely get the electron out. That's like when you threw in the 700 joule rock, and it just barely replaces 700 joules of missing energy the dog had, just barely getting her to the top of the well with how much extra energy? Right, with no extra energy left over. So we replace Ke max with 0, saying that we just have enough energy, just barely get the electron to the edge of the atom with nothing left over. And now we just set them equal to each other, HF equals phi. You can solve for the frequency from there. And if you got confused, you can pause the video, try this, and also do the similar thing for wavelength. So here, I just take that Ke max equals h over lambda minus phi, set Ke max equals 0, so h over lambda is equal to phi. You can solve for wavelength from there. Alternatively, of course, if you found the frequency in the first part here, you just did c equals f lambda to find lambda, that's fine. Just be aware that we want to make comparisons here, right? So we want the wavelength in nanometers. And so if you write it this way, well, it's set up to do it very nicely, because here's h times c, and we just developed the shortcut for h times c. When you do it either way, though, keep in mind, of course, your units. Phi, remember, for silver is 4.73 electron volts, which means which value of h should you use here? Yeah, make sure you're using the one that's 4.14 times 10 negative 15th, because that's in electron volt seconds. If you use the one that's in joule seconds, you're just going to have to convert, or if you don't remember to convert, you're going to get an answer that's completely wrong. So here's what we should be getting. The frequency should be 1.14 times 10 to the 15th hertz, and the wavelength in nanometers is 262. However, if you went a different route, use slightly different values or different order or whatever, you might be getting 263 nanometers. All right, before we end this, one last question. The frequency wavelength here, are these a minimum or a maximum value that will work to just barely get the electron out of the atom? So pause the video, think it through, write down your answers. For frequency, for wavelength, is it a minimum value or a maximum value? So really it's all about the equations, thinking it through, right? Ke max equals HF minus phi. We see that if frequency gets larger, the value of HF gets larger as well, it'll be enough to beat phi, right? So that means the frequency, this is the minimum frequency that will work. Wavelength, well, the equation here is hc over lambda. If lambda gets larger, this whole term gets smaller, and that means it's going to be even worse. It's definitely not going to be the phi. So wavelength there is the maximum. It's all based on the equations, the way the equations are set up and what role they play here, right? As wavelength gets too large, like here, we originally had 200 nanometers, but now we increased it to 500, and when 500 was too large, this value was too small, we, mathematically got negative kinetic energy, which doesn't have any physical meaning, which means that 262 is the largest wavelength that will work, that will just barely get it out, whereas this frequency here is the smallest frequency. Anything larger than it will also work.